All right, so let's see where we're at. All right. So things going on this week, right? We got mastering due tonight and Wednesday nights. We'll do a group quiz on Friday covering chapter 4 stuff. So, yeah, there's no mastering on Friday. I try not to have mastering on Friday just because no one does it. So I just try not to put it on that class. Is it hot in here? All right, so the last thing in the last packet that I skipped, we did stoichiometry, so the last thing in the other one was called dilution. So we'll do a little practice problem. So again, you'll need your calculators out because we're going to do a bunch of calculations today. So dilution. So you did this in lab a few weeks ago, if you remember or not. All right, there was some sort of pre-lab question that had a picture of a beaker that had six things in it, and we'll say if this is a liter. Then I have this other beaker. Now I'm at 2 liters. But I still only have 6 things in it. We'll say moles, that way it makes it easier. So this one has, right, 6 moles per 1 liter. And this one now has 6 moles per 2 liters. How do I simplify that? 6 moles per 2 liters. Warm-up question. Okay, not going well. All right, so 3 moles per liter. So which one is more concentrated? A or B? More concentrated. A is more concentrated, right? What happened between A and B? I doubled the volume and it became more dilute, right? So there was more water, more space for the things to go around. So we can calculate how to do this using the dilution equation, which is not really an equation, but that's what they call it. I think your lab manual wrote it like this, but it's the same thing. Either M1V1 equals M2V2 or C1V1 equals C2V2. That both are fine. All right, M1 is always the starting molarity. That's the concentrated solution. V1 is the volume needed of M1, and that's 99% of the time the thing you're looking for. You're looking for that. You want to know how much of the concentrated stuff to make the stuff you want. M2 is the final molarity. This is dilute. And then this is the final volume. All right, so let's say hydrochloric acid comes standard 12 molar. I would like, or you want, you want 500 milliliters of 0.1 molar. How much of the concentrated HCl do you need? All right, so I'm going to use this equation right here, M1V1 equals M2V2. What do I plug in for M1? The 12. What letter am I looking for? V1, M2, V2. Which one am I looking for? I know M1. I'm looking for V1. Yeah, V1. I'm going to leave that. Okay, so then what's my final molarity? What am I aiming for? Aiming for that. And then that much of it. And you can leave the volume in milliliters. That's okay. Or you convert them both to liters. That's fine too. All right, what's my first step to solve for this? Or all in one? All right, multiply these two together, then what? Divide by 12. Let's see what that is. 0.1 times 500, divide by 12. How many significant figures do I get in my final answer? 3, because we'll assume that I meant the dot there. V1 equals 4.17 milliliters. Yeah. It could be, I could have done liters and liters. That would have been fine, as long as they're the same. That should have been just a little bit of review, because we did that in lab. Right, you had that red food coloring, blue food coloring. All right, any questions on that? All right, in that case, let's start looking at the second half of chapter 4. We'll do some more solution stoichiometry, because that can be tricky. All right, so we have 2 solution stoichiometry problems. This is one of the last things we did on Friday, so these are just some more practice problems to get us thinking about solutions. All right, so we'll do this one first. All right, so according to the reaction below, how many moles of iron hydroxide can form if you have 175 milliliters of 0.227 molar lithium hydroxide solution? And I'm going to go ahead and tell you that there's excess of the iron chloride. So if I tell you there's excess, who is the limiting reagent on the reactant side? The lithium hydroxide, right? So I've already told you that, so you don't have to solve one way or the other. All right, so first question always, is this equation balanced? Oh, question?
Yes, where are you?
I am on the first slide of 4B.
Really? That's not.
All right, I uploaded it on Thursday, so if you print it before Thursday, you may not have this one. Weird. All right. Sorry. The rest of the slides should be fine.
Okay.
Because then I go to aqueous solutions and solubility. Right, everyone should have that one. Big Roman numeral 2. Okay. Because the slides that were on there were review. We already did review. So I figured I just cut out the first 1, 2, 3, 4 slides. One that says review, then says example, then B solution dilution, then C solution stoichiometry. Let's put this in instead. Because we need more practice at this. All right. First, so balanced. Yes? No?
Yes.
Yes. Okay, good. All right, so what is the first step that we need to do, bless you, to be able to use the ratio, right? So if I put in 2 lithium hydroxides, I get out 1 mole of the iron hydroxide. I need to be in moles of lithium hydroxide. So how do I find moles of lithium hydroxide?
Use similar.
Yep. So do I want to start, I guess you can start either way. I'm going to start with the milliliters because that's not the compound unit, it's just a standalone unit. But it needs to be in liters. So how do I need to convert this? Multiply by 1,000 or divide by 1,000? Divide by 1,000. Okay, so 175.0. All right, so what does big M stand for? Moles per liter. So do I put the 0.227 on top or on bottom of this new fraction? Put on top. All right, do you want to stop there or do you want to do it as one big conversion factor? It doesn't make any difference to me. Just keep going. Okay. All right, so now I'm in moles of lithium hydroxide. What do I want to end up in moles of? What is this asking moles about? Right, it wants moles of this. So if I put in 2 moles of lithium hydroxide, how many moles of this do I get out? If I put in 2 of this, I get 1. So I want to put the 2 moles of this on the bottom and 1 mole. That on top, okay. Do I do anything else? Have I answered what it wants? Okay. So 175 divided by 1,000 times 0.227 divided by 2. How many significant figures do I get to keep as my final answer? 3. Everyone get the same answer as me? Okay. I would say for your own best interest, from the entire Chapter 4, you need to be calculating along with me, because Chapter 4 is surprisingly tricky in terms of math. So it'll help you out if you also calculate as well as write it down. Because this is like the easy stuff in the chapter. Then we get titrations. Yeah, question?
The one on the not as updated one,
Yep.
asks for volume. How would you determine the volume?
I would have to give you one more piece of information. I would have had to give you the molarity of the Fe hydroxide, the iron hydroxide. Yeah. Oh yeah, the one that's not updated, that's the one we did last week. We did that one either end of Wednesday or beginning of Friday on last week. All right. Any other questions on that one? All right, let's do the second half then. All right, let's determine the number of grams of hydrogen gas formed when I have 250 milliliters of hydrochloric acid reacting with, that should be a superscript, 3.41 times 10 to the 23rd atoms of iron. I made this as tricky as possible. First question as always, are we balanced? Yes, all right, now we're ready.
That's supposed to be 10 to the 23rd.
Yeah, for some reason my superscript didn't do its thing. I think it's because I'm on a weird font. That should be 10 raised to the 23rd. All right, did I tell you anybody's in excess? What kind of problem is this then? 2 words, one starts with an L. The limiting reagent problem, right? Because you don't know who's in excess, which means you're going to have to solve it twice. Yay! If I tell you it's in excess, then you know who's the limiter. If I don't tell you anybody's in excess, you will have to find moles or grams of hydrogen twice. Preference on which one we get started with? Hydrochloric acid, iron solid? No takers. Is it so cold your brains haven't warmed up yet? Is that the issue? Yeah. Not being from here, I don't get as cold as everybody else. I grew up in Buffalo, New York, and this is like, it's like just first day of school weather usually. Yeah, it's usually snowing on Halloween. Like you'd wear your costume outside your parka. So you had to pick a costume like extra large so it would go on the outside. Otherwise you end up looking kind of like a flasher because like you knock on the door and they're like, oh, what are you? And you're like, whatever. And then you walk off. And so it's, you'd always have to wear it on the outside. All right, how about we do hydrochloric acid first because I'm feeling crazy. All right, do I start with the milliliters or with the molarity? Milliliters, okay. Okay, so step 2. Find the limiting region. I'm all hopped up on candy because my daughter made out like a bandit on Halloween night, and she doesn't like any chocolate candy. She only likes lollipops. I'm like, that's fine with me. I'll go ahead and give you your lollipops, and I'll go ahead and eat the rest. Plus, I thought we'd have a lot of trick-or-treaters, so I bought a lot of candy. We didn't have any trick-or-treaters, so I just have to keep all the candy, obviously. Can't let that go to waste. All right, so we're going to start with, I'm going to go ahead and do the conversion in my head. I'm assuming most people 250 milliliters, 0.250 liters at this point. Okay, good. All right, how do I use the molarity? Do I put 0.74 on top, bottom? Top.
Will it always be on top unless you're finding more?
It should just about always be on top. Yeah, unless we're going backwards.
Yeah.
Yep. All right, so now we're in moles of hydrochloric acid. What do I need to do next? I need to get to moles of what? I want to get to moles of hydrogen. So if I put in 2 HCl's, I get out 1 H2. All right, HCl's on top, so I'll put the 2 mole HCl on the bottom. Am I done with the HCl, or with the hydrogen gas HCl conversion? I can be, right? I can stop here and figure out which one's the limiting reagent and then use it to calculate grams. But since I've already started, I must just go ahead and solve it in grams and then be done with the whole problem. How do I get from moles of hydrogen gas to grams? What do I need to know about hydrogen? It's molar weight. Anyone happen to know its molar weight? It's 1 by itself, and there's 2 of them, so it's 2. All right. Let's see here. 0.25 times 0.743 divided by 2 times 2. All right, so if I start with HCl, I can make as much as 0.186 grams of hydrogen gas. All right. Good. Let's do the iron then. All right. They only give us one thing about iron, so we'll start with that. All right, what do I need to do at this point? If I'm in atoms, right, is this ratio in atoms or in moles? It's in moles, so how do I get from atoms to moles? What magic number do I need? I need Avogadro's number. So, how do I use it? I divide it, right? 6.022 times 10 to the 23rd atoms per 1 mole iron. All right, now I'm already in moles. Excellent. What's the mole ratio of iron to hydrogen gas? 1 1 to 1. So you could not write this down. I wouldn't recommend that. Nope. And then do the same last step. 2 grams of H2 per 1 mole of H2. Moles and moles and moles and moles. All right. 3.41 is 10 to the 23rd. Everybody something like that. For those of you playing along at home. Yeah, okay. All right, in that case, who is the limiting reagent? The iron, the hydrochloric acid.
Wouldn't you need to write that in scientific notation, that last one, like 1.13 times 10 to whatever it is?
I think all the 10s to the whatever went away. Yeah, there shouldn't be any 20. They're all gone. All right, so hydrochloric acid is limiting reagent. So what is the most I can make? 0.1 grams or 1 gram? All right. All right, how do I feel about that? Good, good. It's mostly just unit conversions, doing them over and over again. And you're right, you're going to start seeing a pattern. Like, oh, I'm starting off with milliliters. Okay, then to molarity, then the ratio, then whatever they ask for in the end. Okay, good. We are now ready to do some more complicated stuff. All right, so let's talk about salt dissolving in water versus sugar dissolving in water. All right, so salt, I'm going to say a salt we'll say it's sodium chloride in water. Is sodium chloride ionic or molecular? It's ionic. So when it dissolves into water, what am I going to make? It's going to split apart, right? I'm really going to have sodium ions and chloride ions in water, which is what we're seeing in this picture. Here I have a sodium ion that's interacting with the chloride ion. I also have sodium interacting with the water and the chloride interacting with the water. When I'm talking about solution, what do I call the thing that's being dissolved in the water? It's a special name starts with an S. Solute, right? And so in this case, right, the sodium and the chlorides, those are the solutes. And water is the solvent. So there's two types of interactions that's going to be happening. I have the sodium interacting with the chloride. Those are both solutes, so that would be a solute-solute interaction, right? Those two guys are interacting with each other, and they're both solutes, so solute. I could also have the sodium interacting with the solvent, which would be a solvent-solute interaction. Or the chloride could be interacting with the water. Can I do this all at once? Yep. All right, so both the sodium and the chloride are interacting with the water. Is water polar or nonpolar? It is water, yep. So water is polar, so it's going to interact with the Na plus and Cl minus. As well as with itself. All right, so now we're going to talk about the strength of the attraction. So if I am looking at the sodium and the chloride in the water, if I know in water sodium chloride breaks into two pieces, what is the stronger attraction? The sodium to the chloride or the chloride to the water? If I know for sure they break into two halves. Has to be the chloride to the water, right? This one right here, this must be a stronger attraction than this one. That the chloride would choose to hang out with the water rather than hanging out with the sodium. Which is why they're ionic, right? They choose to break into two ions in water. If I look at a different molecule, such as a sugar solution, which would be C6H12O6 and water. Okay, water is definitely polar, and it is still the solvent. This is still the solute. Well, what do we know about C6H12O6? Is it ionic or molecular? It is molecular, right? It's made up of all nonmetals, so it has to be molecular. If it dissolves in water, is it polar or nonpolar? Right, water's polar, so this has to be polar also. So it's a molecular polar, but it's not ionic, so it's not going to break apart. So if I'm thinking about these interactions between themselves, it's not going to break apart. And it's going to interact with itself more strongly than with the water, right? It prefers to stick together than to break up. So it has stronger solute-solute interactions than solute-solvent interactions. So we could go through every single combination of solutions out there if we wanted to and kind of think through what all the different combinations are, but in general there's going to be some rules as to what's going to dissolve and what's not going to dissolve, and how do we know how much is going to dissolve. So the first is to talk about what are compounds that do dissolve, whether their behaviors, what all do they have in common. And remember, this whole chapter is in water. It's all aqueous solutions, so this only applies to things dissolving in water. All right, so the way ionic compounds versus molecular compounds dissolve in water shows the differences between the types of solutions we can make. So, all right, so ionic compounds, right, made of metal and nonmetal. They're going to always dissociate into in water. They're always going to dissociate. So we have ionic compounds always dissociate into their component ions in water. I'm going to put a little caveat in here. To varying degrees. Right, some completely dissolve and some will partially dissolve and some will dissolve very little. They always break apart. All right, the things that make ions unique is that they're charge carriers, right? So we could think of like sodium plus or that guy or any of those guys, right? They all have some sort of charge associated with them. So if they have a charge, they can conduct electricity. All right, so they can conduct electricity, which we call, in general, an electrolyte. So solutions that have ions in them that can conduct electricity are called electrolytes. Right, which is a very fancy term when you're drinking your sports drink. Right, you got your electrolyte balance. It just means it's salt water of some sort, right? It has to have sodium chloride or magnesium chloride, or you can make your own by drinking some pickle juice or something. Just, has to have some sort of ions in it. Pickle juice is a very common, cheap way of not having to drink Gatorade, but plus it's delicious. Just do like pickles. Anyway, so electrolytes just means it's has some sort of salt dissolved in it. And it can conduct electricity. Which, fun fact, water by itself, terrible electricity conductor. So if you sat in a bath of pure water and dropped your hair dryer in there, wouldn't be awful. You get a little buzz. But it's because you are dirty and you're putting all that soap in there and you're putting everything else in there that the water gets to become an electrolytic solution, which is a great conductor of electricity, which is why you would die if you put don't put your hair dryer in there with you to try this out. But yeah, pure water by itself, terrible, terrible conductor of electricity. So I do a lot of work using water to conduct electricity because I'm an electrochemist by training. And so you have to add salt to the water to get it to work correctly in my work. So water by itself just doesn't do the trick. So. Plus, if you're in biology, you always do stuff with buffers, right? It's the same thing. Cells cannot survive in pure water. They have to have some sort of salt in there to help pass their electricity back and forth from the solution to inside the cell. So, all right, fun facts. Yeah, okay. Yeah, okay. All right, so electrolytes, ions that act as charge carriers in water. Let me make sure I put that in there, in water. So there's varying degrees of how well your ionic solution will dissolve. So solutes that completely dissociate into ions are called strong electrolytes. So this would be, right, the one we just looked at, NaCl, which breaks into sodium and chloride ions. That is a strong electrolyte. It completely dissociates. Or, what's another good strong electrolyte? Potassium hydroxide. That completely dissociates into two ions. So if I have compounds that completely dissociate, I must also have compounds that don't dissociate at all. And we're going to call those non-electrolytes. So if these were all ions, what's the other type of molecule we could have in a solution? Right, these are all going to be our molecular compounds. All right, so sugar dissolves in water, but the sugar doesn't break up into smaller pieces. It stays all together. It just hangs out with the water. Or, what's another one? Yeah, all those would be weird things that wouldn't dissolve in water. Okay. Maybe carbon tetrachloride. No. That would dissolve in water. Okay, I can't think of one right now. But there's other ones that will dissolve in water, but they don't break up. All right, so if I have strong electrolytes and non-electrolytes, I'm also going to have a third category called weak electrolytes. So solutes that partially dissociate are called weak electrolytes. All right, this is my favorite go-to molecule. This is acetic acid. Which, if I'm not mistaken, I think you guys do this week in lab. Are you guys doing titrations this week in lab? Titrating vinegar? All right, no one's read the pre-lab yet. That's all right, lab's not till tomorrow. I'm pretty sure this week you're titrating vinegar. Acetic acid is the main component in vinegar. It is a great weak electrolyte in that it partially dissociates into that. Can't get that weird pink thing. Let's see if that. Nope, that made it worse. Oh, okay. Well, at least now it's on the edge of the screen. All right, so acetic acid is a weak electrolyte. It partially dissociates, which means like half of it stays together, half of it breaks into two ions. Sodium chloride, there is 0 of this in solution and 100% of this. So a strong electrolyte completely breaks up, a weak electrolyte partially breaks up. Let me put another one up here of this. What does anyone know about hydrochloric acid? Any fun facts about hydrochloric acid? It's burny. It is definitely burny. It is a strong acid, right? Considered one of the strong acids. Well, it turns out that strong electrolytes are often strong acids or strong bases. So hydrochloric acid is also a strong acid and a strong electrolyte. Potassium hydroxide happens to be a strong base as well as a strong electrolyte. Sodium chloride, neither acid nor base, so it's just a strong electrolyte. So a strong electrolyte makes a strong acid. If acetic acid is a weak electrolyte, what kind of acid should it be? It's a weak acid. We're getting ready to do some pH stuff. So we're going to start talking about acids, bases, whatnot. All right, questions on any of that? Pretty much just definitions so far. Okay. All right, most ion compounds, when dissolved in water, the solute breaks into ions, right? Assuming it's an electrolyte of some sort. But there are a few exceptions, as always, to chemistry. Not all ionic compounds dissolve in water. So because you guys were so great at memorizing tables of data, I have another one for you. All right, so let's walk through this. We'll do this first. All right, PbI2 is ionic. What would I call it if it's ionic? Lead iodide, right? Lead iodide. All right, so lead iodide is ionic. But does not dissolve in water. Because it's so ionic, right? So when we talked a few minutes ago about whether or not the two ions would prefer to stay together or prefer to float apart, the lead and iodide prefer to stay together. The water, it doesn't have enough ionic strength to pull them apart, so they're stuck. So even though it's ionic, they prefer to stick together. They act like a molecular. So there's no easy way to make predictions about ionic solubility. So we're going to use table 4.1, which is either in your textbook or in your handy-dandy PowerPoints. All right, so this is table 4.1 out of your textbook. All right, this is a weird looking table, so let me walk you through how to read this, and then it'll make some sense. All right, so soluble compounds are things that dissolve in water. Right, soluble means dissolve in water. So they're saying just about anything that's stuck to a sodium or a potassium or an ammonia dissolves in water. Just about anything that has a nitrate, chlorate, perchlorate, or acetate dissolves in water. Those are all givens. Just about anything that has a halide, a chloride, a bromide, and iodide dissolves in water. Unless you put a chlorine with a silver. That no longer dissolves. So exceptions in this first half mean insoluble. So if I put silver with chloride, not soluble. If I put mercury with bromide, not soluble. Or lead chloride, not soluble. Just about everything that has a fluorine attached to it should dissolve. Unless I've stuck it with one of these guys, one of those 5, which is the alkaline earth metals, or lead, because lead's weird. And just about everything with a sulfate should dissolve, unless, again, I stick it with one of the alkaline earth metals, calcium, strontium, barium, or lead. That guy, lead. All right, so that's the top half of the table. The bottom half says everything in here should never dissolve. Carbonates don't dissolve, phosphates don't dissolve, chromates don't dissolve, sulfides, hydroxides, unless I either put them with ammonia, or which column is the alkali metals? The first one. So if I stick, wherever I just put that, KOH. All right, KOH definitely dissolves. Even though it says hydroxides don't. Oh, wait. K is in that first column. All right, that dissolves. You're going to need to actively learn, maybe with some flashcards, these guys, because there's really no straightforward way of knowing these. But they're super useful. All right, we'll do these 4 examples, and then we'll stop for today. Determine the insoluble compounds using our little table. See if I can have them both on here somehow. All right. So I have silver chloride. All right, so just about everything with the chloride should dissolve. Oh, nope, I stuck with the silver. Not soluble. All right, sodiums just about always dissolve. So that looks good. Is there anything on here that prevents me from saying sodium nitrate dissolves? All right, there's sodium. Here's nitrate. They're both in this section. Yep, soluble. All right, lead chloride. All right, chlorides always dissolve. Oh, wait, I stuck it with lead. Pretty much if there's lead in there, it's not going to dissolve. So lead chloride, not soluble. All right, barium hydroxide. All right. I know hydroxide. Okay. Hydroxides are not soluble. Unless it's barium hydroxide. That one is soluble. I mean, that was a gimme, right? Because I already had not, then yes, then not, then last one yes. So, all right, we will stop there. We will start to predict using chemical reactions. We'll play the game. Will it dissolve? Huh? That sounds fun.